Okay, so I have my variable station temp, and I want to just take the average January through April temperature from this for the years of 1980 to 2013. And the way I do this is I can basically just type JFMA, new variable, January, February, March, April, temp equals, and I'm going to take the average over the first dimension of the data, which is months, station temp, and just the first 4 months. And then what I'll do is I will take only the years of 1980 to 2013. Now, the first year of data is 1895, and so I'm going to subtract 1980 minus 1894, which would result in the right index of years to extract from. So 1980 to 2013. Okay, and then I'm going to average over the first dimension since that's months. Okay, so that's going to give me the right sort of data to use. Now what I'll do is I will go to one of the websites, and here what I'm doing is I'm going to extract and copy and paste in the data for the NINA 3.4 index. And here I'm only going to take the data from 1980 to 2013 as well, and I'll just copy and paste this in since that's simple enough to do in MATLAB. So I'll start here with 1980, and I'll just copy all these lines all the way down to 2013. Okay, copy it, bring it over to MATLAB, set up a new variable name, Nino34 equals open square bracket, paste, and close square bracket. Okay, and then what I'll notice is if I look at the variable that I just created, it's 34 years by 13 months. That first month is just the year increment. And so for this exercise, all we really care about is just the January data. So that's the second column here, right? The first column is year, second column is January, third column is February, etc. So Nino 3.4, just January, I'm just going to extract that from the larger matrix of data. And so that's all years and just that second column. Okay, so then I can just look at the variables that I have in memory here. I have Nino 3.4 and I have JFMA temp. So those are the two variables that I'm going to be plotting here. And so I will make a plot of these variables. So Nino 3.4 JFMA temp. Oops, and that'll be plotted up. And I'll look at where that figure is. So here is that figure that I just made. So it is a scatter plot. The data is obviously quite scattered. Okay, that's fine. Immediately when you make a scatter plot, you can quickly see whether or not there is some relationship or if there is no relationship. And in this case, I see really a cloud of data, nothing really strong. But nonetheless, you can continue to carry through your analyses. So when making a scatter plot or making any sort of figure, it's always important to add in labels to your figure so that your friend actually knows what in the world they're looking at. So we'll add on the Y label here, and in this case this is temperature, JFMA temperature. California is my station, and here the units are in degrees Fahrenheit since I did not convert. And I'll make the font size a bit bigger so that it can be legible. And then I also will add in an X label. So the X label here is just the Nino 3.4, Nino 3.4 index. Okay. So that's pretty much it in terms of the plot that I made here. And one thing to notice is that we have a cloud of data. We can calculate the correlation of this data, and that can be done by a function called core that you've used previously. So we'll do a core of Nino 3.4 and JFMA temp. Doesn't matter, you can type them in JFAM temp for comma Nino 3.4 or vice versa. And when I did this, immediately I got an error message. And the reason for that is because they have a slightly different size to them. So here you'll see that One is 1 by 34, and the other one is 34 by 1. So that's just obnoxious. And so what we can do here to correct that is to just invert one of them. And when I do that, I will get an R value and a P value that get returned to me. So the R value is the Pearson's correlation coefficient. So this is telling me the linear relationship between the two variables. A correlation of 0 means that it's total and utter garbage. It's completely uncorrelated. A correlation value of -1 means that it's perfectly negatively correlated. In other words, for every x increment in the Nino 3.4 index, there will be a subsequent decrease in the JFMA temperature. And then a +1 value is a perfect positive correlation. So here we have a negative correlation. It's a negative 0.27. And if you look at the scatter plot here, if you had to draw a line to fit this curve, you probably would draw a line that's going in a negative direction. So that's why we have a negative correlation. The p-value here tells us something about the statistical significance of that correlation. And what we find here is the p-value is 0.122. So that basically says that we would get this sort of a correlation, by chance, something on the order of a correlation this low by chance, or a correlation this low or this high by chance of maybe around every around 12% of the time or so. So it says there's some correlation, but we generally find that this is not a significant correlation. When the p-value is less than 0.05, that usually is considered statistically significant. In other words, we would not expect that correlation to happen except for every, say, 5 out of every 100, random samples. So in this case, we have a negative correlation, but it's not statistically significant. Okay, so that's what you would report for this particular exercise. And then finally, what we can do is, for the bonus exercise, what we can do is actually build a statistical model of this. So it takes on a very similar form, except here we'll actually be affixing numbers with the relationship. We'll actually be drawing a line through this data. So to do that, what I'll do is use the function polyfit. So this is fitting a polynomial. Nino 3.4, Nino 3.4, JFMA temp, and we're going to use a polynomial order of 1, which is just a linear fit. Okay, so we'll do that, and then what we'll do is look at our value of A. So this is basically what's returned to us from this equation, and this is basically saying what the coefficients of a linear equation are. So we know, like, a linear equation looks something like this: y equals ax plus b, right? That's sort of y is the model we're trying to fit, a is the slope of the line, and b is the intercept. So what happens here is that a is basically this first value, and b is the intercept. Okay, and that's what basically we'll actually end up modeling that here. Okay, so what we can do now is we can we'll actually hold this plot on, and then we will create a slope to this line. We'll actually use the model we developed and force that model to run with some data that we created. So we'll use polyval of A, which was that's the rise over run and the intercept, and then we'll use data that goes here nominally between -3 and 3. So that'll basically span from -3 on the x-axis to +3 on the x-axis. Okay. And then finally what I'll do is I will make a plot. So I'm going to plot a line onto this graph here, and the plot will be from -3 to 1 to 3, and it will be AA. And I'm going to make this plot red and make the line a bit wider so that it is legible. Okay, so there's our line on the plot, right? That's basically our model, right? You can see it's not great. In fact, our model has quite a bit of error to it, and that's okay. Again, we only used one predictor variable here, and this may not be the best predictor. Right, we're using the Nino 3.4 by itself to predict temperature in the sort of the deserts of Southern California. So you see there's some relationship, but it's not extremely strong. The final piece to this is that we have a model here, and we can actually use this model in a forecasting sense. So for this past winter, we saw a very weak El Nino or La Nada, El No-Show developing. The Nino 3.4 index as of December 1st was about negative 0.7. Okay, so you could eyeball where negative 0.7 falls on this line, or we could use the MATLAB interface here to just tell us what the value of our model would be for an El Nino index of negative 0.7. We can just type that in here, and it returns us a value of 66.02 degrees Fahrenheit. So that would be our prediction based purely on the Nino 3.4 index.